All right, everybody. So let's go over page 3 of our week 2 concept check. And the first thing we're going to do is predict the type of decay. So it turns out if we have a radioisotope, we can decide what type of decay it's going to undergo, alpha, beta, or positron. So a couple things to point out, right? We're going to be looking at Z, A, and what I'm calling A dot W with decimals. And so remember, if you have an isotope symbol, let's just do something generic here. So I've got a symbol, I've got A at the top, Z at the bottom, right? Remember that this is mass number and this is atomic number. And so when you go to the periodic table and you look at the box, atomic number is going to be there, but mass number isn't, right? But under the symbol, that's where you see your atomic weight. And so we're going to take advantage of the fact that the atomic weight is going to be due to the stable forms of that particular element. Because again, most atoms have a stable nucleus. And so the first step that you're going to look at is to look and see whether or not Z is greater than 83. And so if yes, you're going to get alpha decay. And so remember, alpha decay is losing 2 protons and 2 neutrons. And so it makes sense that we would get alpha decay, because if we have something that's really, really big, alpha decay gets rid of a small part of that nucleus and works it back towards the belt of stability. If you have something smaller, what you're going to do is compare the mass number to the atomic weight. If you have a mass number that is bigger, that would be referred to as something that is neutron heavy, right? Because again, all the isotopes of a particular element have the same number of protons. What differentiates them is the number of neutrons. If something has a mass number bigger than the atomic weight, it has extra neutrons. And it's going to undergo beta decay, which makes sense because remember that in beta decay we are turning a neutron into a proton. Now, if we have something that's got a mass number less than the atomic weight, it's neutron light, it falls below the belt, and so it's going to undergo positron decay. And remember, positron decay does the opposite. It turns a proton into a neutron. So these make sense, right? If you have something with extra neutrons, it undergoes beta, which turns a neutron into a proton. If you have too few neutrons, it undergoes positron, which turns a proton into a neutron. So all of these steps will force things back towards the belt of stability that has the stable nuclei. And so going through this, and by the way, these are the first 3 from the online exercise where you're predicting. What you want to do is simply use your periodic table and the first thing you want to do is look at your element, silver, iron, radium. Go to the periodic table, look up their atomic numbers. Silver's element 47, iron's element 26, radium's element 88, and from that you can look at step 1. So right away I notice that radium has a mass number, has an atomic number that is greater than 83. And so because of that, I know that it's going to undergo alpha decay. For the other 2, I need to look at the periodic table and look up their atomic weights. Again, I use the colored periodic tables at the back of the exercise book and the course materials book both, right? It's got all those pretty colors, and underneath there you will see a decimal number. In the case of silver, it's 107.87. In the case of iron, it's 55.85. And now all I have to do is compare the mass number to the periodic table. And so for silver it's 105, for iron it's 60. If that mass number is bigger, it's beta, right? If your isotope has a bigger mass number than the atomic weight, it has too many neutrons, bigger is beta. I love when there's alliteration. Now, if the opposite is true, if what is on the periodic table is bigger, then you have positron. Because what that tells you is my silver 105 doesn't have as many neutrons as a typical silver atom. It's neutron light. It's going to undergo positron decay to turn one of those protons into a neutron. So that's it. Those are the simple steps to predict. Basically, you're just trying to see where your isotope falls in relationship to the stable isotopes for that element. Is it too high? Is it too low? Or is it something that's way beyond the belt? All right, the bottom of our sheet 3 here is looking at the types of decay or the types of chemical nuclear reactions we're going to see in part 2 of our nuclear chemistry lecture. And one of the things you should realize is you can balance fission, fusion, bombardment reactions using the same skills as before. But we do want to talk about kind of what's going on here. So you can see the definitions. Fission is taking a big nucleus and breaking it apart into 2 smaller nuclei or more. Fusion is the opposite of that. It's taking smaller nuclei and building them into a larger nuclei, fusing those 2 together. Bombardment is any time you have a nucleus that's been hit with a particle to create a new nucleus. And then a potential chain reaction happens when you hit that nucleus with a particle, you cause some reaction, and you get something here. It could be fission or fusion, but the key is you get 2 or more of the same particle that was your bombardment particle. So let's look at some examples. So what you want to realize is, again, think about what your top number is for your side that you have everything on. So I have everything on the left-hand side. But on the right-hand side, I've got 88 plus 3 times 1, right? 3 times 1, which is equal to 3. So I have 88 plus 3 plus whatever I'm missing should add up to 240. On the bottom, I've got 37 plus 0, because again, 3 times 0 is 0, plus whatever I'm missing should add up to 94. And so in this case, I take 240 minus 91, and I'm left with 149. On the bottom, 94 minus 37 is 57. And I go to the periodic table, and I see that element 57 is lanthanum. I can do the same thing with my others, right? So for the second example here, I add up these. I get 262. I get 103 when I add up the 98 and the 5. On the right-hand side, I basically have 5 times 1 or 5 and 0 on the bottom. So the top is going to be 262 minus 5, which is 257. And on the bottom, I'm going to need all 103. And then I go to the periodic table and see that that is Lr, or lawrencium. For the third example, 13 plus 1 is 14. 7 plus 0 is 7. I already have 4 on this side in the top, so I need 10 more to get to 14. I already have 2 on this side, so I need 5 more to get to 7. Element 5 is boron. So again, we're just balancing the top and the bottom numbers on the two sides of the arrow, right? The two sides of the arrow need to be balanced. Now, the question is, are these bombardment reactions, fission reactions, or fusion reactions? And so what you want to do is kind of think about what you have. And so label each of your terms as either a nucleus, right, which is anything bigger than a particle. So that's a nucleus. That's a smaller nucleus. That's a smaller nucleus based on the atomic number. And then we also have a particle here. And we also have a particle on the right. So the question is, does this fit the definition of bombardment? Yes, having a particle to the left of the arrow means that you have a bombardment reaction. And so you can have a bombardment reaction that is fission, that is fusion, that is neither. Right? Bombardment is just something that gets this type of reaction, nuclear reaction, started sometimes. Then we can also ask ourselves, is this fission or is this fusion? It can't be both, but it could be one or the other. And in this case, because we have a big nucleus breaking down into two smaller nuclei, I'm ignoring the particles here, this is also a fission reaction. If we look at our second example, we have a nucleus and a nucleus, and we're making a bigger nucleus. We also get some particles out, but those particles are on the right-hand side. There's no particles on the left, so this is not bombardment. And in this case, we're dealing with fusion because we are taking two smaller nuclei of 98 and 5 protons, and we are creating a larger 103 proton nucleus. So this would be considered fusion. Now the third example here is in a gray area. And it's in a gray area because boron is definitely a nucleus. The question is, do you call this a nucleus, a helium nucleus, or do you call it an alpha particle? And so we're going to call it a particle. Again, not everybody agrees, but we've been in the habit of calling an alpha particle a particle. We're going to continue with that. And so if we call it a particle, this is classified as a bombardment reaction. If you call it a nucleus, you could call this fusion. And so you'll see when you go to balance the bombardment reactions that you have in your exercise book that oftentimes an alpha particle is the bombarding particle. So there you go. That's our week 2 review. Hopefully now you feel confident in doing homework number 2. Don't forget it's both sides. And as always, thank you for your time.